Hey, thanks for watching my video today. It's about polar moment of inertia and center of gravity and how you take those into consideration in RC airplane design. You can email me at stefan@migsrs.com. Check out our blog at migsrs.com, also rcpowers.com, and then RC Flight School I'll refer to as well. The AMC is a collaboration between Scott Challoner and I. We have a new recent addition, Dave, but we are interested in furthering the science and design of RC airplanes. Well, if you've been reading our blog, there's been a lot of Easter eggs, and maybe you picked up on those in some of my presentations. We've been doing a lot of research and development. We're up to about 1,000 test flights in the last 9 months, and I've spent about well over 100 hours moving pixels in iDraw trying to develop the ultimate MiG. Here's our inspiration, the MiG-29. It all started with the RC Powers V3. This is a picture of my MiG-29 V4 from RC Powers. So Scott and I decided we really wanted to make the ultimate foamy park jet. Early on, we noticed a couple bad tendencies. The elevon polar pitch effect. This is where you put the airplane up on its side. Because of the huge surface controls and elevons on the tail, a little bit of wind, and it made that airplane weather vane all over the place. Another one was what I call T-vol, thrust vectoring blank wagon, and that's where you trying to do some high alpha or come into a carrier and you get too much throw in your controls and essentially stalls out your thrust, and then the airplane starts twerking all over the sky, you lose control and crash. So in determining what modifications we're going to make, I read a lot of aerodynamic text, went to Wikipedia, and trying to figure out the true science behind the aerodynamics of these airplanes. Well, one thing that we've come full circle and realized that you have to have the concept that this is a precision aircraft. This is a park jet. It's designed to fly precisely. It's not a 3D plane. It's not an edge. It's not an extra. It doesn't need insane throws. It doesn't need high expo. And the park jets, as all other airplanes in RC design, and David Scott brings this up in his book, Airplane and Radio Setup, that this whole 3D concept has creeped and moved into the regular RC world. And these clearly, the surface creep contributed to the EP and T-vol that we saw early on in the V4 and the V3. So we've really changed over this concept of precision flying, precision design, CG, polar moment of inertia. If you don't have this book, you've got to buy this book, Airplane and Radio Setup. This really should be your go-to book. It explains all these concepts of CG, balance in airplane, how to set appropriate CG, servo resolution. It's a wonderful book and it should be on your workbench. But the big concept that came out of this book for me was maximizing servo throw to utilize your whole mechanical advantage. So in this precision revolution, we've done this, applied this to the servos, applied it to the throws. And I even went back in my old airplanes and converted them to precision type settings rather than the 3D settings they had. It was like flying a brand new airplane. I had a lot fewer of those blank moments of EP and T-vol, and it was like flying a whole new airplane. It really was a wonderful experience. Along with that came determining the proper CG on an airplane, and then when it came to the design, polar moment, inertia, and balance. So here's what we're striving for: a nice looking airplane that can just rip up the sky with wonderful surface control, precise agility, tactical advantage. And here's the latest concept, the MiG-35. This is what we're striving for. This look, this airplane, just a better all-around MiG-29. So what do we have to do with our ultimate MiG? Well, we shortened the plane, improved the scale appearance, and we also found the true CG. Lowered the polar moment of inertia tremendously. Along that come positive negative effects. I'll talk about those more later on. But in terms of CG, the RC Powers, I mean, you know, you've got to make a plane that's good for everybody. So they're nose heavy CGs, and that's more beginner centric. There's a lot more stability in the airplane. With a large PMI and a little bit forward CG. And a lot of people just like to fly at this feeling. But once you discover a true CG on an airplane, you'll discover that that's actually opens up a whole new possibilities in terms of precision flight and control. And then we wanted to lower the polar moment of inertia. Now doing this does narrow the CG window. And if you have a very forward CG, we found this out early on, but on a plane with a tight polar moment of inertia, you get into bad problems quickly. So it's an entire concept. Everything all works together. So going on in CG, I always went with the plans, and then I read on the blogs, if your plane flies at no trim at 40% throttle, that's the good CG. So that's how I flew all my planes. But realistically, if you think about it, these planes are ridiculously overpowered. 40% throttle with no trim, that's really controlled propulsion, not balanced flight. If you think about the big airplanes, the faster you go, the more air over the wing, the more the lift. The more the lift, the more down trim you need to fly the airplane. So at different speeds, you're going to have different trim requirements. So you find out where you like to fly your plane the most, and after you set the CG, then you trim it in at that speed that you fly the most. Really, these are rockets that turn. Let's talk about polar moment of inertia. There's two analogies, the egg carton and seesaw. I did not think this up. Think about an egg carton. You've got 4 eggs. Put the 4 eggs in the middle, put your finger in there and spin the carton. It's easy to spin. Now take those 4 eggs, put 2 at each end and try to spin it. It takes a lot more effort to spin. All right. So in an airplane, it's the same way. The 2 big components we have in the move are the battery and the motor. So if you can tighten the battery and the motor up, you lower the polar moment of inertia, which means it's easier to turn about its axis or its CG. Let's take a little bit more concept talking about lever arms. So think about it. You've got 2 people at the very ends of a seesaw. It's a lot harder to move that seesaw up and down. You put them in the middle of the seesaw, it's very easy to move them. So that's your lever arm. Okay. So a plane with a very short PMI has a very long lever arm, which means it's easy to rotate about its axis. But the shorter the lever arm, the more energy it takes to rotate the plane. But here's where you see the yellow airplane that's got the long lever arm. So imagine now you've got that airplane up in the air sideways with that long lever arm versus the short one of the white airplane. A little bit of wind has got that longer lever arm, which is going to make the plane rotate more about its axis, or what we call EP, than the airplane that's got the longer PMI. So a shorter lever arm requires more force. That's why servo resolution is so important, that you want to maximize your mechanical advantage. So I talked about earlier that rotational force, the longer the lever arm, the less force it takes. So the tighter the battery and motor length, the lower the polar moment of inertia, but it is more prone to EP. But all things constant, EP is still going to be more noticeable with a lower PMI. But in this plane, and taking that consideration, we also shorten the over length to decrease the size of the tail surfaces, so we reduced that effect of lower PMI by reducing the surface area of the trailing elevons. Bring in one more concept about center of lift. This gets a little bit more difficult to understand, but on an airplane, the horizontal stabilizer provides a negative down lift. The wing provides upward lift, and you've got the fuselage itself. And actually in the MiG, 40% of the lift is provided by the fuselage itself. 60% comes from the wings. So all these combined lift forces create what's called the center of lift. Some people like to call it a center of pressure. So when the airplane's flying, all these things add up to push against the bottom of the airplane in one place. And ideally, you're going to have that center of lift very close to the CG, or have your CG a little bit in front of that. That makes for a nice, stable, predictable airplane. So when you think about it, you're flying your airplane, you get a little slow, you lose lift, that center of lift all of a sudden is gone, moving back. The nose drops, you gain speed, the airplane comes back to level flight. All right, that's where your CG is correcting with your center of lift. Now, a neutral plane will tend to fall off. A neutrally balanced plane will fall flat, and a tail-heavy plane gets very difficult to control and falls tail first. So think about that distance between that CG and the center of lift is a lever arm as well. So if you've got a very forward CG on two airplanes with the identical PMI, that lever arm is longer, and it's going to make that plane more susceptible to ebb if you don't have a CG lined up with your center of lift. That's why center CG is so important on this new MiG that we've designed, that everything's got to line up for precision flight. Now the ultimate test for CG is a glide test, but I personally don't want to go up to second story windows and throw a MiG out the window that I spent a week building and then watch it crash into the ground because I had it totally wrong. So easy way to do this is what I call the arcing maneuver. And there's different things you can do and read about on the web, but this is very simple. I take the plane about 40–50% throttle, climb at about 30 degrees, cut the throttle, and let go of the controls and see what the airplane does. It should continue to ascend and then make a very gradual, nice transition to descent. It's going to eventually stall at the top, but a little bit heavy CG or neutral is going to come down and regain speed and then continue to glide. You can also just go level and do this, but I found if you're doing it on ascending, going up, it gives you more room for error, or you need to start up high when you do your level test. And then if you really want to get down to the nitty-gritty of it, you need to do an inverted flight test as well to make sure that the plane flies equally at the same throttle inverted as in regular flight. But a lot of people find inverted flight a little more difficult, and we're not all that, some of us aren't as good as others at flying our airplane inverted. So think about a lower PMI, the plane rotates quicker around the CG. That translates to increased agility and precision. The plane will yank and bank and turn faster, is much more precise and a lot more fun to fly. Now, it does come with a decreased stability, but it's well worth the trade-off. And that is why, because the stability part is so important to dial in properly a true CG, to have precision surface controls and throws, maximum servo resolution, and not have a high-speed jockey plane like this loaded up with 3D type surface controls and throws. One last analogy to help you understand how these, if you've got two moving objects, you see there's Lewis Hamilton in his F1 car and there's Jimmy Johnson in his NASCAR. Think about IndyCar and F1 cars if you ever watch racing. When they break loose, it's a violent, quick snap, and the cars are difficult to regain control. The NASCARs, when they slide, it's this big, long, slow slide maneuvers. The NASCAR's got the engine at the front, transmission at the front, and then just the differential at the rear. Very long PMI. The F1 car's got the very, very short PMI. Everything is compact towards the middle as much as possible. So that's the difference in terms of stability and how they recover. So a plane that's got a very long PMI is great for straight and level flight. Cargo, passengers, it's going to be a nice, smooth flight. It's hard to get it to change attitude. But a short PMI is going to give you tremendous tactical maneuverability advantage. You can do rapid changes in direction. And remember, on your planes, your CG is a starting point. You've got to verify your CG with flight testing because planes with a short PMI is very important. So here's kind of the evolution, the V4. Gone through a few prototypes here. Continuing to make changes, moving things around, searching for that ultimate combination of CG, PMI, surface control, size, as well as settings. Here's the latest plane I'm developing as well. This is what I call the MiG FA. The FA project was a stealth project where MiG as well as Sukhoi came up with stealth aircraft, Sukhoi 1 with the T-50. So I'm kind of combining the best traits of the MiG along with the T-50, and I just call it the MiG FA. This is my version 2, and it's a project in evolution as well. So stay tuned. RC Power is going to have a lot more coming up. I've given you a few Easter eggs to think about. They're also putting together another video talking about calculating center of mass in search of 3-axis balance, and that's what I'm doing right now with the MiG FA, and looking at vertical CG instead of just longitudinal CG. You can email me if you have any questions at Stefan@migsrs.com. Visit our blog site at migsrs.com. Don't forget to go to RC Powers, get your V4 package, and stay tuned for upcoming planes. and get the book from David Scott at RC Flight School. Thank you very much.